Oh my gosh, I must have looked like such a dork. Do my nostrils flare? Want some fish? Hi Morgan. So the first thing I did when I got your email was delete the labels and change them to x1, x2, x3 up to x7 because this way I was doing the test blind. Then using your table of data, I created my own, just entered the quantities of the number, the right amount of time. So the next step was then to put an x squared column next to each of the x1, x2, x3. And this is how we're going to get to our sums of squares. So I can enter in the formula and then just copy paste all the way down, all the way over, make sure I label things. So now that that's done, I'm going to relabel this so we can stop scrolling up and down all the time. And next I'm going to create sums going all the way across because this will give me the sum of x and the sum of x squared for all 7 x's. So there's the sum of x1 and the sum of x1 squared and the sum of x2 and the sum of x2 squared all the way to 7. And finally, I'm going to take the sum of all x by adding up those 7 boxes and the sum of all x squared by adding up those 7 boxes. So the next thing I'm going to do is copy over all these sums that the computer so nicely found for me. To begin with, n for group 1, or the number of participants in group 1, is 50. The sum of x1, 277, and the sum of x1 squared, 1705. n2 is going to be 50 also. There's 50 in each group. Sum of x2 is 204, sum of x2 squared is 1004, and 350. Sum of x3, 266, sum of x3 squared, 1691, and 4 is 50, sum of x4 is 110, sum of x4 squared is 370, n5 is 50, sum of x5, 291, sum of x5 squared, 1925, n6 is 50, sum of x6 is 242, sum of x2 squared, 1328, and n7 is still 50, with sum of x7 being 261 and sum of x7 squared, 1507. We should also copy down the sum of all x, which was 1651, and the sum of all x squared, which is 9531. So now I draw our favorite handy dandy chart and decide that I think I'm going to do sums of squares total first, because that's the formula you should be most familiar with. Sums of squares total equals the sum of x squared minus the sum of x squared over n. Using our numbers, that means 9,531 minus 1651 squared over 350 equals 9531 minus 778800. You should be checking this math, by the way. And I get a total of 1743 even. So I'm going to enter that in the chart. So next comes the sum of squares between. Sum of squares between equals the sum of x1 squared over n1 plus the sum of x2 squared over n2. You keep going until you've gotten all the way to all the groups. So in your case, it'll be the sum of x7 squared over n7. And then you subtract the sum of all x squared over the total number. So when we plug in the numbers, we're going to get 277 squared over 50 plus 204 squared over 50 plus 266 squared over 50 plus 110 squared over 50 plus 291 squared over 50 plus 242 squared over 50 plus 261 squared over 50 minus 1651 squared over 350. Crunching through those numbers, I get 463.34, and I'm going to write it over in the chart, but you should be checking these yourself. So now we have to do sums of squares within, which is going to be the sum of x squared minus that whole big quantity we did before. So the sum of x1 squared over n plus the sum of x2 squared over n. all the way out till we get to the number of groups we have, which is 7. And replacing that with numbers, it should be 9,531 minus 277 squared over 50, 204 squared over 50, 266 squared over 50, 110 squared over 50, 291 squared over 50, 242 squared over 50, 260 squared over 50. And I get 1,279.66. So we're going to bring that number over to our table, enter it in, and the lovely trick with this table is we can add straight down. Does 463.34 and 1,279.66 add up to be 1,743? Yes, so that means we can move on. So now degrees of freedom. The degrees of freedom between groups is equal to k minus 1, and you'll remember that k stands for the number of groups we have. So that's going to be 7 minus 1 equals 6. Put it in the chart. Degrees of freedom within equals the total n, so n sub t, minus k, and your total was 350 minus k, which is 7, 343. Put it in the chart. And degrees of freedom total is the total n minus 1. So that should be 350 minus 1 is 349, and add that to the chart. Just like sums of squares, we can do the same addition to check our work right here. Is 6 plus 343 equal to 349? Yes, so we get to move on. And the rest of this, you won't believe how easy it is. So the formula for variance between is equal to the sums of squares between divided by degrees of freedom between. So we just divide straight across. 463.34 divided by 6 equals 77.22. And the same thing goes for the variance within. It equals the sums of squares within divided by the degrees of freedom within. So straight across, that's going to be 1279.66 divided by 343 equals 3.73. And our final step, to get f obtained, we take the variance between over the variance within, which means we can just put a little line right here and get 20.7. And that is our f obtained. That's what all this work was getting us to. Uh-oh, she's bringing out the stats textbook. Okay, so you remember about the elusive charts in the back of the book that I've been talking about all the whole time and never really mentioned because it was irrelevant because we weren't really doing any tests? Well, guess what? Now we actually need to look at the mysterious charts in the back of the book, which I first need to find. Aha, so here's my book. You see the F distributions. Okay, so along the top it says between groups degrees of freedom. And our between groups degrees of freedom, if you remember, is 6. So, lucky for us, there's a column over here that says 6. Now along the side, they have to do the within groups of freedom. And for you, the within groups of freedom is 343. So we got up to 23. So my book goes up to 100, 200, 1,000, and infinity. So just to be conservative, we're going to do 200. And for a 0.01 alpha level, which is only a 1% chance that we're making a mistake, so that is super conservative, you needed to obtain an F of 2.89. Right there. Now, for your viewing pleasure, here is a blown up version of the F distribution. Over here is where 0 would fall, and the 2.89 that we just found is our F critical. I'm going to draw right here. So, if our obtained value falls within this portion, the pink portion, we have to retain our null, which means, and the null was the neutral statement, right? So that would make that true, which means we don't get any results. But if it falls over here in the green area, we get to reject the null, meaning that the research hypothesis has to be true since they're mutually exclusive, and we found results. And your F obtained of 20.7 falls way off the charts. So very clearly, your F obtained is higher than your F critical, and you can reject the null. So that means we have significant results. That means we can reject your null hypothesis, which was back a couple videos ago, and we can say, oh my goodness, yes, some results occurred. Some of these samples were rated differently in terms of taste. Unfortunately, that doesn't tell us which samples, but I need a break. Do you need a break? There are two more things we gotta do, so let's see how fast we can do them. The first thing is effect size. Effect size can tell you how much of an effect the independent variable really had. For ANOVAs, effect size is eta squared, which is the ratio of the sums of squares between over the sums of squares total. And that would be 463.34 over 1743, so that gives us an eta squared of 0.27. And this only strengthens your hypothesis test by proving that you have a high effect size. Now I'm going to come back to my spreadsheet from earlier and create a row for the means. So I can just take the total of x for each row and divide by 50. So here I'm getting 5.54, 4.08 for x2, 5.32, 2.2, 5.82, 4.84, and for x7, 5.22. I'm just going to jot this data down and use it for the next step. And the last thing is the post-hoc test, which I mentioned briefly yesterday. So after you run the ANOVA and get results, then you have to run one of the post-hoc tests in order to figure out between which groups are there actually results. So one of the least conservative tests, and my favorite, is Tukey. Tukey, honestly significant difference. That's what he named it. Anyways, the formula is the mean of one group minus the mean of another group all over the standard deviation of the means, which is also known as error. And you find that by taking the square root of the variance within over n. So that's going to be the square root of 3.73 over 50. That's the square root of 0.07 or 0.27. And so that we can fill in for the standard deviation of the means for all these formulas. So coming over here, let's just start by comparing x1 and x2. Alright, so I'm going to do 5.54 minus 4.08 over 2.7, and that gives me 5.41. And then for x1 and x3, 5.54 minus 5.32 over 0.27 equals 0.81. So you get it's the same pattern over and over. I calculated you have to do it 21 times, but we'll use a low alpha level. Technically, you're only supposed to do it for the ones that look like they will come out to be significantly different, because you don't want to waste some of your precious error on ones that won't work, but I was curious, so I did them all. Okay, so x1 and x4, 1237, x1 and x5, negative 104. It doesn't matter if the numbers are positive or negative. Negative just means that the one in the front is the worst one, and a positive number means the one in the back was the worst one. Alright, x1 and x6, 2.59, x1 and x7, 1.19, x2 and x3, negative 4.59, x2 and x4, 6.96, x2 and x5, negative 6.44, x2 and x6, negative 2.81, x2 and x7, negative 4.22, x3 and x4, 11.56, x3 and x5, negative 1.85, x3 and x6, positive 1.78, x3 and x7, 0.37, x4 and x5, negative 13.41, x4 and x6, negative 9.77, x4 and x7, negative 11.19, x5 and 6, 363, 5 and 7, 2.22, and 6 and 7, negative 1.41. Okay, so now I once again go into the back of the book where there is a chart for the Tukey test. It's measured in Q. And so for an alpha level of 0.01, so this is conservative. So we're using the non-conservative Tukey test, but with the conservative alpha level. our results need to be more extreme than plus or minus 5.01. So that means x1 and x2, x1 and x4, x2 and 4, 2 and 5, 3 and 4, 4 and 5, 4 and 6, and 4 and 7. But I also want to include x2 and 3 and x2 and 7, kind of, because had we not been so conservative, those ones would also show significant results. So now I've consolidated the ones that have honest, significant differences according to Tukey, and we have to figure out what this is actually telling us. So I see that in all of these, x4 is the worst one. So that means whatever x4 stood from was significantly worse than all the other samples. Similarly with x2, it's worse than x1, it's worse than x3, it's worse than x5, and then x7. So now is when we finally, after all my math is done, go back to your email and I see, okay, well, x4 corresponded to the recipe with no sugar. So the no sugar recipe is significantly worse than all the other recipes. And x2 is the no egg recipe, so that's significantly worse than the original, the no milk recipe, the no gluten recipe, and the no chocolate recipe. So now it's time to type up the conclusion. What can we practically apply from this? Well, we can't for sure say which cake recipe was better, but we for sure as hell can say which two recipes were worse. So if you are allergic to eggs or diabetic, sorry, we haven't found a good cake recipe for you yet. But the good news for people on low-fat, gluten-free, dairy-free, or chocolate-free diets is that those recipes don't taste significantly better or worse than the original. So they shouldn't feel like they're missing out on anything. Is that what this experiment was all about? I think that's what this experiment was all about. Hoo-Haa, nerd fighters! With my nerdy chest decorations here, and my nerdy Tetris decorations over here. Aw yeah, nerd fighters to the max.